Hello, so in this video we're going to be looking at something called increasing and decreasing functions. Okay, where am I going to start? Let me consider this graph y is x squared. Right, pretty standard graph. You would have seen even at GCSE, the quadratic graph, right? So y is x squared. Now, what we're going to then consider is where the function is going down and going up. Imagine it's like a roller coaster, right? Imagine, or a slide or something like that. Let's say someone is at the end here, or at the start here. Well, then they're going to go down, right? They're going to almost slide down. That shows the function is going down, or in other words, the function is decreasing. Okay. Then when they reach the 0 at the origin, then they start. Then the curve goes back up. Okay. And so then you can imagine the person will be climbing up, right? Something like that. The curve is going up, right? So after 0 at the origin, the curve is going up or it's increasing. Okay, that's what we're going to be looking at, right? So if I was to highlight this, right, let's say, so this works. Red firstly. Okay, so the curve we say is decreasing when it's going down. So we always start from left to right. So then from the left it's going down in this region here until it reaches 0. Then it flatlines, right? Goes to 0. Then after 0, the curve goes back up. Okay. So if I do that in yellow, then the curve is going up. Okay. And so hopefully you can see that these two graphs, they're decreasing in the red part and then increasing in the yellow part. Okay. So if I use a different colour, let's say red, this is decreasing, which means it's going down, and increasing in the yellow part, which means the curve is going up. Okay, that's essentially all we mean by increasing and decreasing functions. Where's the curve going down or decreasing in value, and when is the curve going up? Okay. Let me then look at this example here. Let's then highlight in this other example here. Let's highlight where the curve is going down and up. So firstly, again, we're going to start from the left side because obviously the graphs go from left to right. So until this turning point here, this minus one, that turning point, hopefully you can see the curve is going down like a roller coaster, right? So this is in red, so it's decreasing in this part of the graph here, right? Then what about after it reaches this point here, minus one? Hopefully you can see the curve is picking back up. Then it's increasing from minus 1 until the origin, till 0. Then it starts to level off. Then it's going down again like a roller coaster. So then it's decreasing after 0 until the second point here, and then it's picking back up again. Okay. And so then we got two. So then you can see we've got two regions where the graph is decreasing, which is in red again, and two regions where the graph is increasing in yellow. Right. So decreasing and increasing in yellow. So hopefully you're with me so far. So simply, if we go from left to right, we study where the graph is going. So is it going down or up? All the way throughout from left to right. Okay. And so this is the idea of decreasing and increasing functions, right? Okay. And so actually we can be a bit more detailed with this and give exactly where the graph is decreasing and increasing, the values of x, where it's decreasing and increasing. That's mainly what we're going to be focusing on in this section. So when is it decreasing? Okay, let me do that in red again. Well, firstly, this point is when x is minus 1, right? This point is where x is minus 1. And this point is where x is positive 1, right? So the values of x, first of all, when it's decreasing, it has to be less than minus 1, right? Use it in red. So decreasing. Well, firstly, it's decreasing when x is less than minus 1, but actually it could be equal to minus 1 as well. Because if it's when it's equal to minus 1, it's 0. It's not increasing or decreasing per se, because it's flat, right? It's at the point where it's going from decreasing to increasing when x is minus 1. So we can include it, because the idea is, as long as it's not going up, that's still decreasing, right? But we'll talk more about that in a minute. But x is less than or equal to minus 1. And then the second region here, when it's at 0, and then the second point at 1. So then it's also decreasing in the second red region here, between 0 and 1. And that's my region, okay? I can do the same for increasing in yellow. I forgot to highlight it, this bit in yellow. Well, the first region then, the first yellow region where it's increasing now, so we're looking for the values where it's increasing. Well, firstly, that's between minus 1 and 0, right, from when x is minus 1 and 0. And for the and then this region here, right, when x is greater than 1. Okay, so after when x is 1, then it increases again. And that's my region. I will write this in black as well. It might yellow might not be easy to see. So the two regions. So this region, this yellow region, was between minus 1 and 0, and the other yellow region, which is there, right? That region is when x is greater than 1. Okay, greater than or equal to 1. So that's my two regions of increasing and decreasing. Okay, so hopefully you can spot essentially where graphs are increasing and decreasing, right? Simply when the graph goes downwards and when the curve goes upwards, right? Okay, so that's the core idea. And then we could do the same for this as well, right? So decreasing for this x squared graph, wow, it's to the left of 0, so x has to be less than or equal to 0, and it's increasing on the right side when x is greater than or equal to 0. And so the idea is, you can see we're giving values exactly where the graph is increasing or decreasing. It's quite similar in the idea when we solve quadratic inequalities, where we give the values of x for certain regions of the graph. That's kind of what we're doing here. We're finding the regions of the graph where it's increasing and decreasing. Okay, cool. Now obviously we're in the differentiation chapter, which is to do with gradients. Well, where does that come into play? We've not looked at gradients yet. Well, we know the idea of increasing and decreasing functions, but how can we sort of mathematically sort of write it or work it out, right? How can we mathematically work it out rather than just looking at the graph? Because sometimes we won't have the graph, right? And it probably could be quite difficult by hand to sketch a graph. Okay, let me consider this. What we're going to then consider is, with my ruler here, I'm going to consider the gradients along this curve here, from the red part to the yellow part. Let's see what happens. So we're going to start here, at this point here. If I draw the tangent to the point there, it's steeply going down, right? The ruler, the tangent is negative, right? It's quite negative. It's steeply going downwards. Okay, then let's consider this second point here, in the middle part here. If I draw the tangent to the curve there, it's starting to become less steep, right? Something like that. So it's still negative, it's still going down. My ruler line, my tangent, still negative, my gradient, but it's starting to become a little bit less steep. Let me then consider this point over here, right? This third point there. If I then draw the tangent line to that point I've circled, it will look something a bit like this. Something like that. And again, it's negative, but I'm making it less steep now. It's becoming less steep, but it's still negative. Okay, what happens then when it becomes 0? Okay, bang on 0. What would the tangent look like? And so actually at 0 it would just be a flat line. Okay, as so. Okay, so what's happened, hopefully if you just look at that, what's happening is, as we're decreasing until we're increasing, what's happening to the gradient is it's negative, the gradient, but it's becoming less and less steep until the line is flat, until there's no gradient. So the gradient is negative until it becomes 0, until it's flat. Okay, let's do the same for increase, and now let's try to draw the tangent now at that point on the yellow part of the curve. So you can see it's starting to increase now. I'm starting to make it steeper and upwards, so it's become positive. Okay, and it looks something a bit like that, right? So again, now it's increased, so it's a positive because the tangent, my ruler, is going upwards now, not downwards. Okay, then let's consider the end point here, the other end of the curve here. And then again, you can probably predict I'm going to need to make it steeper. Okay. And there we are. But it's still going upwards. It's still up, right? So my tangent, my gradient is positive. Okay. Okay, so it's quite interesting then. So if I summarise what we just looked at, when we're in the red part, when we looked at these points on the red part of the curve, the decreasing part of the curve, my ruler, my tangent, my gradient was negative because it was going down. Which makes sense, because if the curve is going down, then my gradient has to be negative, right? And likewise, when it was increasing, it then made my ruler go up, so it became positive. My gradient is positive, okay? And actually, the steeper the curve is, the steeper my gradient is, which again should make sense. So really, we can actually then consider gradients to actually kind of translate this more precisely, right? So with our little experiment here, you could see that actually, firstly, if f of x is increasing or decreasing, then that means that the gradient, right, on the decreasing curve, on the decreasing part of the curve, the gradient is negative when the curve is going down, which means as the gradient is the derivative, so f dash of x, if it's negative, then it's going down. Okay, so it'd be a negative gradient. Okay, and we can write it like this. Okay, similarly, if f of x is increasing, f dash of x is greater than 0 there. Okay, but actually, again, I could also include 0 as well, because 0, as we saw, 0 is a special point. We will be looking at that point. So 0 here at the origin, as we saw, the tangent was exactly 0. It was completely flat, right? So it's not increasing nor decreasing exactly. So we can pull it as either or. Okay, so we can include points that are neither increasing or decreasing per se there. So you can see it's completely flat, right? So it's not decreasing or decreasing exactly, right? Not one or the other. So we can just include it really here. So we can include if the derivative is 0 as well, if the line is completely flat, okay? Because again, if it's flat, it's not really increasing or decreasing, so we could have it included, right? But we could exclude it, right, by introducing this idea of strict inequalities, right? So remember, a strict inequality. So for example, if we had 6x was greater than 9, that's a strict inequality because it's not strictly equal to. If it was equal to, then it's just, I guess, like a standard inequality. But we can make it strict by removing the inequality. So a strict inequality is an inequality that is not equal, does not have an equal sign. So we want to exclude 0. We can also say if f of x is strictly decreasing, which means we strictly want the curve to just keep going down. We don't want it to level off. We don't want it to go to 0, the gradient. We don't want it to stay where it is. If we want it to just keep going down and down and down without any sort of stopping, right, then it's strictly decreasing. It strictly keeps going down. And then that means, because it's a strict inequality, that f dash of x would be strictly less than 0. Okay, so it'd be negative, the gradient, right, because it's going down. And likewise, if f of x is strictly increasing, f dash of x is greater than 0. Okay, strictly greater than. Okay, so that's sort of what we're going to work with, right? We're mainly really going to work with this sort of these two statements. From what I've seen, they're not overly fussed, at least at A level, about how this sort of preciseness of the inequality. So you really mostly expected to know this, but I thought I'd give a bit more detail about strictly decreasing and stuff like that. But really, as long as you recognise that inequality there. So decreasing and increasing. Decreasing if the gradient is negative, which means the curve is going down. Increasing if the gradient is positive, which means the curve has to be going up. Okay, cool. So now we have a mathematical way of showing things are increasing or decreasing, right? Now, the last thing we need to talk about, and it isn't really to do with this topic, but it's a more general thing, and it's another bit of notation, okay? And it will be relevant to this, but a bit of notation you need to know. Well, actually, in reality, with a simple curve like this, obviously it's quite clear where the decreasing and increasing parts are. It's a simple inequality, but in reality, what happens is the curves are going to keep going up and down, up and down, up and down at various points. Okay, it's not always just going to go decreasing, then increasing, and that's it. You're going to have points, you're going to have regions in the curve where it keeps decreasing, increasing, decreasing, increasing multiple times, like in this example here. And so what happens is we have multiple different inequalities or values of x. That then we need a more sort of succinct way of expressing inequalities, and this is where something called interval notation comes into play. And it really again, it's not as bad as it looks. But okay, if we have an inequality where x is between a and b, let's say, again it could be equal to a or b, then we could say this is the interval. This is the interval AB with square brackets, okay? So for example, if x was between 2 and 5, then this is the interval, or x is in the interval 2, 5, okay? 2, 5 with square brackets, okay? So when you see square brackets with sort of two numbers like this, a comma b, 2 comma 5, that means it's between 2 and 5, okay? Again, it's a bit of notation to express inequalities, okay? So we can express inequalities in this interval notation as well. And again, this goes back to our idea when I talked about strict inequalities, because again, with this interval notation, we can also write down strict inequalities. So what if x wasn't equal to a or b? So if we have a which is strictly less than x and strictly less than b, then this is the interval sort of round brackets a and b, okay? And so hopefully obviously the difference here is that the brackets are different. So this is a square bracket, which means it's inclusive, which means it includes a and b at the end. And if it's a round bracket, that means it excludes a and b at the end, but everything in between a and b. Okay, so it's strictly between a and b. Okay, so for example, let's go back to our example. If 2 was less than x less than 5, then x is in the interval 2, 5, okay, with round brackets, okay? So yes, you do need to be able to read what this interval stuff means. So if you see these square or round brackets, you need to know what that means as an inequality, okay? So overall, the square brackets means it includes, say, 2 and 5, but with round brackets, it doesn't include 2 and 5, so it's a strict inequality. We could also mix and match, okay? So for example, if we then had said 2 was less than or equal to 5, but x was also, no, 2 less than or equal to x, but x was also less than 5, strictly, then we could say x is in the interval square bracket 2 at the end at 2, but 5 and then a round bracket, okay? So you can see the idea that a round bracket is a strict inequality and the square bracket is an inclusive inequality. So we include 2, so it's a square bracket at the 2, and it excludes 5, so it's a round bracket at 5, okay? So hopefully the core idea is that round brackets exclude it and square brackets include it, okay? Right, okay, now we've got that out the way. Let's have a look at some questions then. Okay, so we're told in this example, firstly, show that the function f of x, which is x cubed add 24x add 3, is increasing for all real values of x. So what we can do then is use the idea of the derivative. If it's increasing, then it has to be greater than or equal to 0, okay? So if it's increasing the function, then its derivative has to be positive, okay? So greater than or equal to 0. Well, then let's compute the, let's work out the derivative then, right? So f dash of x, well, if we differentiate our function then, well, x cubed firstly goes to 3x squared, 24x goes to 24, and the number 3, it's just a number, so it goes to 0, okay? We've seen that before when we differentiated certain functions. So there we are, so that's my derivative. Now, I need to show that this is greater than or equal to 0, this expression here, which would then mean it's increasing. Okay, well, think about it then. That's what we want to do, but think about it. Well, firstly, the x squared has to be positive, it has to be at least 0. It can't be negative because it's a square number. So I'm going to say x squared has to be positive as x squared is a square number. And so therefore 3x squared will be greater than or equal to 0. But if I'm adding 24, that means it has to be at least 24, right? Because 3x squared has to be at least 0, because if x squared was 0, then the minimum would be 24, because we add in 24 on, okay? Very similar to when we did similar proofs with completing a square. We can use completing a square form to show that the square number x squared is at least 0, and then we can show it's above 0 or something like that. So it's at least 24, but we want to show it's greater than or equal to 0, so that means it could also be greater than 0 as well, okay? So that means it's increasing. So f dash of x is greater than 0, so f of x, so not f dash of x, but f dash of x is the gradient. We've shown that the gradient was positive, which then means the original function is increasing, okay? Make sure you are very aware of the difference, right? The f dash of x is the gradient, which tells me if it's positive, then the function is increasing. We want to show that the function is increasing or decreasing, not f dash, okay? F dash, we look at the sign, okay? If it's a positive, if f dash is positive, then the function is increasing. If f dash is negative, then it's decreasing, okay? And so f of x is increasing there, okay? Because the gradient is positive. Right, and that's all it is to it. Technically, it would be strictly increasing because it's strictly greater than 0, but again, usually they're not that bogged down with that specific detail. But so yeah, okay, cool. Let's have a look at this question. Now, this example says find the interval, which is going to link back to what we talked about with intervals, right, at the start. So we're going to find the interval for which the function f of x, which is x cubed plus 3x squared minus 9x, is decreasing. So we want to find where it's decreasing. So again, we can consider the sign of the derivative, and actually if it's decreasing, it would be negative, so less than or equal to 0, okay? If we were to do that then, so that means it's decreasing, let's compute the derivative, right? So the derivative, if we differentiate the function, by x cubed will go to 3x squared, 3x squared will go to 6 plus 6x, and minus 9x will go to minus 9. Now we need to show it. We need to find where it's decreasing, which means it has to be less than or equal to 0. Okay. Right. Well, actually, if we were to solve this, this is just a quadratic inequality. At this point now, hopefully you realise this bit is a quadratic inequality, which we saw how to solve earlier on in the course. So let's solve this then. The 3x squared plus 6x minus 9 is less than or equal to 0. So firstly, I can actually just divide by 3, because all the terms have a 3 as a common factor, just to make it easier, right? So then x squared add 2x minus 3 is less than or equal to 0. Okay, so now we want to find my critical values, right? Because remember, I want to sketch this quadratic. So my critical values, well, I need to solve it as if it was an equation, right? Obviously we've got an inequality, but let's pretend we're solving. So x squared add 2x minus 3 would equal 0. So I don't know, you can do whatever you want, however you want to solve it. Does factorising work? Well, we'd need two numbers at times to get minus 3 and add to get positive 2. So the factors of 3 are just 3 and 1. And actually, yes, because if I do positive 3 and then minus 1, 3 minus 1 is 2, and 3 times minus 1 is minus 3. So that's my factor. So x plus 3, x minus 1 equals 0. So that means my two values are x is minus 3 or x is 1. So now I can do a rough sketch of this sort of quadratic, right? So x squared plus 2x minus 3. I know my roots are at minus 3, and my other root is at 1. So now I can do a rough sketch, and it's a positive quadratic because the x squared coefficient is positive. So it would look something a bit like this. And there we are. Now, okay, cool. So we sketched it. Now, we need to go back to our inequality. It's less than or equal to. So we want the part of the graph below 0. So it's going to be underneath in this region here. So what values of x bound that region? Well, it's between -3 and 1. So we can say that x is between -3 and 1. And it could be equal to, because the inequality is inclusive, right? And that's it. So that's my solution. So so that's my solution, right? So therefore, x -3, x is less than or equal to 1, or because remember the question said as an interval, okay, not as an inequality or a range of values of x. It wants an interval. So we need to use them square or them brackets, right? Well, if it's inclusive, it's between -3 and 1 and includes it. So we can use square brackets of -3 and 1 as an interval. So that means so -3 and 1 with square brackets is the same as between -3 and 1, okay, as an inequality. Okay, so yes, you do need to be comfortable. You need to be aware of intervals like this to write down inequalities. Okay, and there we are. Okay, we're going to look at some more exercises now. So we need to show that this function f of x is 4 minus x times 2x squared add 3 is decreasing for all x in R. So remember we talked about that we talked about this before, that x, this notation means x is a real number essentially, right? Because this means x and then this sort of e symbol means is a member of, and R with that sort of font is the list or the set of real numbers. So again, there is there's some notation you do need to be aware of that you might not have seen at GCSE, like with the interval stuff that we just seen. Over time, you'll get used to it. But yeah, so that's what this statement means. All it means is x is a real number, okay? Now, okay, let me get rid of that then. Anyway, the idea of the question then, let's not get sidetracked, is the function is decreasing, okay? So how do we show it's decreasing? We need to show that the derivative then is less than or equal to 0, okay? As it's a negative gradient, okay? So let's work out the gradient then. Well, firstly, f of x is 4 minus x of this. We can't differentiate this because we have x's together. We need x's by themselves. We can only add stuff together. We can't multiply stuff yet. In year 2 you will see that, but for now we can only add x's. We can't times them when we differentiate. So let's just expand the bracket then. So it's going to be 4 minus 2x cubed minus 3x, and now they're all as just individual powers of x, right? All x's by themselves. So now we can differentiate this expression. So 4 goes to 0, then minus 2x cubed will go to minus 6x squared, minus 3x goes to minus 3, and that's my derivative. Now I need to show it's decreasing, or in other words, less than or equal to 0, this expression here. For all values of x, right? So I need to show no matter what, this is always less than or equal to 0. Well, actually, I notice I can factor a negative out. I can factor negative 3 out. So negative 3 of 2x squared add 1. Okay, can I then now see that this is going to be negative or less than or equal to 0, right? Can I see this expression is going to be negative? Yes, because again, this idea of a square number, 2x squared has to be greater than or equal to 0, as x squared is a square number, and if we add 1, then overall this has to be greater than or equal to 1, right? But then I'm timesing by a negative, right? So then I can say that 2x squared, so as x squared is greater than or equal to 0, as it's a square number, then then well then I can say that minus 3 lots of 2x squared add 1. Well, if the bracket has to be at least 1, then that means if you times by negative 3, it has to be below minus 3. Okay, we're always going to get a negative, right? So it's going to be below minus 3. Okay, or negative. Okay. So I can just say is a negative, or must be negative. Hopefully you can see that, right? Because this whole expression has to be positive, because x squared is a positive. I'm just adding positive numbers. So again, this whole thing has to be at least 1, but then I'm timesing by a negative number, right? So a negative times a positive is a negative. So therefore, f dash of x has to be greater than or equal to 0 for all x, for all values of x. Well, what does that mean? If the derivative is always negative, then that means the function has to be decreasing. And there we are. Our proof is done. So now we've shown that it has to be decreasing by considering the gradient, and we've shown that the gradient was always negative. Okay. So always do another. So again, a very common sort of trick, or not a trick, but a tactic is if you want to prove certain inequalities or signs, if it's positive or negative, it might be helpful to consider the fact that a square number, x squared, has to be positive by default. Okay. So we've got this question now. We are told that given that the function f of x, which is x squared add px, is increasing on the interval minus 1 to 1. What does that mean? Minus 1 to 1 is a square bracket, so it includes these two numbers. As an inequality, we could say x is between minus 1 and 1, right? So remember, inequality, interval, we can convert to an inequality in this way. Okay, so okay, that's what the interval means, between minus 1 and 1. X is between minus 1 and 1. We need to find one possible value of p. So again, the function is increasing for these values of x. So firstly, obviously if it's increasing, the derivative has to be positive. Okay. So then let's work out the derivative. So if we differentiate this, that's going to be 2x, and then px goes to just plus p. And so if it's increasing, we want to consider greater than or equal to 0. Now, this is where this inequality is going to kick in. So it's asking to find one value of p. So we kind of want to solve for p. So let's get p on its own. So let's rearrange this a bit by subtracting by 2x. So p is greater than or equal to minus 2x. Now, x is between minus 1 and 1. Let's see what happens when x is minus 1. Let's sort of substitute that in. So then p is going to be greater than or equal to minus 2 times minus 1 for x. That would be plus 2. So p has to be greater than or equal to 2. What if x is then 1, okay, at the other end? So then p would be greater than or equal to minus 2 times 1. That's minus 2. So these two things have to happen. So that means p is greater than or equal to minus 2, and p has to be greater than or equal to 2. Well, actually, this one is redundant. If p is greater than or equal to 2, then by extension it's also greater than minus 2, right? Because minus 2 is less than 2. So this is actually quite unnecessary. So that actually, therefore, p is just greater than or equal to 2 is my solution here. Okay. And so that if we want to find one value of p, well, I don't know, just take p's 2. I don't know. So, for example, p is equal to 2. Okay. Then part B then says, state with justification whether this is the only value of p. Well, I mean, I don't know. We just seen that there are multiple solutions because p is greater than or equal to 2. So we deduce that p is greater than or equal to 2. So can take any value greater than or equal to 2. Don't know, quite a weird question. I've also seen the mark theme for this, just to roughly check, because I thought it was quite a weird question. The mark scheme says basically what I said, all the answers to the solution. It's quite a weird question. Okay, some of the textbook, right? Some of them can be a bit weird, but hopefully you get the idea, right? We found the increasing part by setting the derivative to be positive, and then we sort of solve for p in a way. Okay, so we've got some exam questions on this then. So firstly, we're given the curve with equation y is 3x squared at 24 over x at 2. Now for part A, we need to differentiate. We need to find dy dx. But before we do that, we need to deal with this fraction 24 over x. I need to rewrite that as a power right before I differentiate. Well, 3x squared and then this 24 over x, we can write that as a negative, right? As a negative power of 24x to the minus 1 at 2. And there we are. So now we can differentiate, use the power rule. So we bring the power to the front. So 3x squared, rather 2 times 3 is 6. X, and then we knock 1 off the power. Then we do minus 24 as minus 1 comes to the front. X, and then we subtract 1, knock 1 off the power. Minus 1 is minus 2. And then the 2, the number at the end goes to 0. And that's what we're left with. Okay, then part B, it says hence find the exact range of values of x for which the curve is increasing. So curve is increasing when what? The derivative, or dy dx, is positive, right? There. Greater than or equal to 0. Okay, so the gradient is positive. Okay, so hopefully again you start to get used to the idea that now that decreasing means the gradient is negative and increasing means the gradient is positive, right? That's all we're really using here. Now, we've already worked out the derivative, right? So then we can say that 6x minus 24x to the minus 2 is greater than or equal to 0. Now we need to solve that equation to find the values of x. Okay, so this index, I'm not too sure what to do with it, right? As it is, so let's kind of use the power laws to almost convert back as a fraction. So then we can say 6x minus 24, but x to the minus 2 is a reciprocal of x squared, right? And that's greater than or equal to 0. Now actually we've seen, we can now, what can we do here? Well, we've seen, obviously you might be thinking that's times by x squared, right, to get rid of the fraction. You'd be right, but I imagine there's some skepticism because of an inequality. You might be thinking, oh god, if it's positive or negative, what happens to the inequality? You might maybe a bit of a freak out. We did look at examples like this before when we solved quadratic inequalities. But because x squared is a positive, right, it goes back to the idea that squared number is positive, we preserve the inequality sign. So if we times by x squared, that's fine. We can times by something squared to keep the inequality where it is. We're allowed to do that. Okay, so if we times everything by x squared, we would get 6x cubed minus 24 greater than or equal to 0. Okay, then we can solve for x, right? So then 6x cubed is going to be greater than or equal to 24. So then x cubed is greater than or equal to 24 divided by 6. Now that goes to, that does simplify to 4, actually, quite nicely, to 4. Well, then, how do we get x? We can just cube root. And again, the inequality stays where it is because we're not square rooting to get plus or minus. Cube rooting, we just take the positive. So again, the inequality stays where it is, okay? So we can cube root both sides and we get this solution here. Okay, and that is my exact range of values of x. So x has to be greater than or equal to cube root of 4. Cool. Okay, we've got this final question then. It's a bit trickier, but we can work with what the ideas that we've learned. So we're given this sketch of a curve. We're told it's a cubic. We're also told some information about where it passes through. We're told all that information on the diagram though. I'm not going to read that out. We are told firstly to find the set of values for x for which f dash of x is less than 0. Well, this is kind of working backwards. So now you should recognise that this is saying the gradient is negative, right? What does that mean? That means the function has to be decreasing, right? So if it's a negative gradient, then we can go back, we can go the other way as well and say that as a result it's decreasing, okay? And actually, technically speaking, it'd be strictly decreasing because it's a strict inequality, okay? But the idea is it's decreasing. So the values of x then, well, we just look at the graph, right? Where's the graph decreasing? So again, we read from left to right. So from the left at this point here that we're given, let me highlight again. So the yellow for is increasing, right? It's increasing at that point until this point 2.8. Then it dips down, okay? So then it's decreasing, it's going down until this point at 6. And then it shoots back up, okay? And it just shoots and it just keeps increasing from there. So the only part that's decreasing is the red part, right? And that is between the x values. Well, this point, go back. This point here is when x is 2. Right? And this point here is 6. Okay? That means the values of x, the set of values of x for which it's decreasing, or strictly decreasing, is between 2 and 6. And and again, it's a strict inequality, so it's strictly between 2 and 6 because it's a strict inequality we're given, okay? And that's it, okay? So that's the idea of part A. We can just look at where the graph is decreasing to give me the values of x that way, okay? Now, part B then says we're given a line with equation y is equal to k and it intersects the curve at only one point. Find the set of values of k in set notation. Okay, so this isn't really to do with what we've learnt this video, but again, it practices the idea of graphical intersections, which we looked at before. So what's essentially going on? This line y is equal to k. That's the line y is equal to k. For example, if y was equal to 1, it would look something like this. If y was equal to 7, it looks something like this. It's a horizontal line, okay? It's a flat line. So it would look, if I use my ruler to sort of use this line, it's going to look like a flat line like this. Okay, and so the idea is, it's saying that this line y is equal to k, which is basically represented by my ruler here. This line intersects the curve at only one point. What we need to do then is to basically kind of use a ruler to kind of visualize where the curve is intersecting with my line only once. Hopefully you can see down here there's only one intersection. It's intersecting with the yellow part on the left here, right? Then if I keep moving up, then it hits the point x is 6 there. At that point, then there's 2 intersections with the curve, okay? And then there's 3 intersections, right? There, there, and there, right? So that's not what we're interested in. Oh dear, didn't mean to get rid of it. Now there's 3 intersections after it reaches 6, and then it reaches the top of the curve on the left at this point 2.8. At that point, there's only 2 intersections. Then, when we go beyond that, now there's only 1 intersection where it's on the right side of the curve, right? Well, So there are two regions then really where my line, my line, which is y is equal to k, there's only one intersection. It's so if I draw a straight line there from 2, 8, so that's the point here. Anything beyond the point of circled there, that's only one intersection. So I want values bigger than this, and also below 6, okay? Because then if it's below 6, if I keep going down, then there's only one intersection point on over there. So I want my values then to be above, well, y is equal to k. So I want my y values to be above this point here. That's going to be, the y value is 8, right? So that would be 8. That would be 8 there. So above, y is equal to 8, and below, y, well, it's going to be the x-axis, right? That's where the point 6 is, right? So x is 6, so it's below the y-axis, right? So it's below the x-axis, sorry. So it's below y is equal to 0. So then that means that y, as inequalities, then we could say that y, if it's above 8, y has to be above 8, and no, it could be or, okay, or y is less than 0. So if it's below y is 0, as we've seen, then it's one intersection, so it's y less than 0, and y is greater than 8 when it's above the line y is equal to 8 to get that as well. So that's my answer, but it asked me to give it in set notation, which means I need to use my curly brackets, which again we looked at before. That was in linear inequalities. If you need a refresh, I did a video on that. So as an inequality, remember the idea with set notation with these curly brackets is I can only have one inequality at a time, okay? So firstly, the values of y such that, and then y is greater than or equal to 8. So I copy my inequality, right? But I can't then say or y is less than or equal to 0 in the same sort of bracket. I need to split it up, okay? And so what I'm going to say then, or, remember, is this union, right? This U shape, that means or, and then we introduce another bracket, another set of y such that y is then less than 0, okay? And there we are, that's it in set notation, okay? So again, the idea is being that we split up the inequality, these two inequalities, separately into two different sets, okay? And apologies, I've just realised that it's solving for k. I'm not solving for y. Y is equal to k, but we want to find the values of k. So I should say that actually k is greater than or equal to 8, or k is less than 0. And so my set is k such that k is greater than or equal to 8, greater than 8, or k such that k is less than 0, okay? We're solving for k. So yes, apologies. That's the final full solution, the proper solution. Okay, cool. Right, that's part B. So again, hopefully it's a very visual question, that is. Hopefully you visualised what was going on there, okay? And my ruler being, obviously, when it's below the x-axis, that there's only one intersection. Then when it's above this line y is equal to 8, then again there's only one intersection on the right side of the curve. Okay, part C, we want to find the equation of C, okay? So now, if I get rid of my annotations on here, so we need to look at my graph. It's asking for the equation of the curve, but we're given the roots, right? So it's kind of like the factor theorem. I know the roots are at 0 and 6. So if I use factor theorem, I'm basically saying y is going to equal to x, and then my other factor is x minus 6, right? Because remember, my two roots are x is 0, x is 6. So if they're my roots, then my factors are x and x minus 6. But there's two things. That's not the complete equation. But first of all, you'd be able to tell it's not the right equation, because that will give me a quadratic. okay? It's a cubic, not a quadratic. So again, you need to go back to when we looked at sketching cubic graphs, and a key property we looked at was the roots. And if the root was touching the x-axis at this point, so it's touching 6, okay, that is a double or a repeated root, okay, if it touches the graph, the axis at that point. If it just touches the root like this, rather than just passing through it like at the origin, it just goes straight through it. If it's just touching it, then it's a repeated root, which means the factor has to be squared, because it's like double, right? So that's what I mean by repeated. Its factor is twice. So actually that would get me a cubic. But this is the other thing we need to consider. There would also be a numerical factor as well. This gives me the algebraic factors, the x's, but there will also be sort of like a scale factor, an a, right? There, okay? So we also need to account for the fact there could be another number, a factor a. That's because these roots, these factors, come from solving the equation equal to 0. But the problem is, we need to account for the fact there could be a number as well, right? Because then what we could do is we could then divide both sides by a. Then x of x minus 6 squared would equal 0. That'd be perfect. That'd be fine. Then we would get x is 0 or x is 6, which are my roots. Which I know they are my roots. I've already seen, right? They're my roots. So you need to be careful then when you're going backwards, when you're given the roots, to then find the factorisation. You need to account for the fact there might be a number factor as well, because of the fact we can just divide by the number and cancel it out in this way. Okay, so there is another factor a as well. Okay, and there will always be a factor a if you're doing it in this way. Remember, we looked at examples like questions like this when we looked at the graph sketching chapter in chapter 4. But here we are. So there's going to be a factor a then as well because of this. So y is equal to ax of x minus 6 squared. That is my equation. My mission now is to find the missing value a. And I can use a point to substitute into. I know this point lies on the curve, right? 2, 8. If x is 2, y is equal to 8. That's my point on the curve, 2, 8, right? If that point on the curve, I can substitute into my equation to find a. So therefore, y is equal to 8 of a times x, which is 2, times by x minus 6. That's 2 minus 6 all squared. Then 8 is equal to, then if I do 2 times 2 minus 6 squared, I get 32. So that's 32a. Therefore, a is 8 over 32, which is a quarter, I believe. Yes, a quarter. So my final equation, my complete equation, is y is a quarter x of x minus 6 squared. Okay, and there we are. Cool. And there we are. Okay, so that's increasing and decreasing functions. And I'll see you next time.